And let's see if we can get started. So there's a couple principles to look at, as you can see. And one of the, I'm going to read, there's no sense in me, I might as well read it with you. One of the things, of course, is resolving power, the ability of a lens system to separate fine detail. It's not sharpness. A lot of people use the word sharpness, and so that's as a matter of fact, the word sharpness, there's no objective definition of it. Sharpness is subjective. Like you look at a picture of your friend and you say, boy, that picture is detailed and sharp, but there's no mathematical definition for that. But there is a mathematical description of resolving power. And so when we talk about resolving power, what we're talking about really is resolution. In fact, these two words are almost the same. Resolution. But resolution usually is where you calculate it. So it's the smallest resolvable distance between two objects. And there's a formula. Let's see what we can do with this. Notice the formula. So sometimes we use the sometimes we use the letter D and we say distance equals 1.22 times lambda over 2 NA. That's the formula. And yes, you should know the formula for the test because the performance objective says you should be able to calculate this. What is lambda? Lambda is the wavelength of light. And I don't expect you to know that, but I can tell it to you. And it's approximately, white light is approximately 5,000 angstroms. So I must give you that number. I do not expect you to know it. And so that's what we put here. Numerical aperture comes off the microscope. So we've got to go back to the microscope for just a moment. Oh boy, I guess I should have. Okay. I'm going to clear it. Let's go back to the microscope. Now, these are 3 objective lenses, and you'll notice there's a 4x, a 10x, and a 40x on them. That is the power of the objective lens. Very important. The power of the objective lens. Let's look at the real picture. I don't think you're going to be able to see it no matter how much big I make the screen, but etched on every objective lens are 2 numbers. There are 2 numbers. One is the power of the lens. And the other one, let's see if we have anything better. No, I can't quite see it. We might see it on one of the pictures we have later. Even if I enlarge this, I don't think I'm going to see it. But on each objective lens, there are 2 things that are there. So it would be right in this area, right in here. One of the things on the objective lens will be the magnification or power. I'll use the word let's use the word power. Now I can tell from looking at this, because I know the microscope, that this should be the 40x lens. So I'll just write that out here. So when you use a microscope, all you have to do is look at the objective lens. There may be 3 or 4 of them. If they have oil lens, they have 4. You just look at the lens and read right off the objective lens what's there. Now, I'm hoping I picked that right. If not, it doesn't matter because you'll obviously write down what you see. Also, you might not see it. Also, there will be something else there. And I better pick, I'm going to move my arrow here. Let's go over to this one because I know this one right off the top of the head. So the power is 10x. And there's something else etched on each lens. I don't know it for each one, okay? But I do know it for this one. There is something else there. And the other number is going to be the numerical aperture, which is 0.1. Well, that is written on this lens. The power, which is, gee, did I make another mistake? The power, which is not doing so good today. The power, hopefully I can get back my, where'd it go? Yeah. Well, try that again. There we go. The power, which is actually 4x. And I'm going to get rid of this other one. So we're going to work with this lens. This is the shortest lens. It's the one with the red band. And that's true for most microscopes. The red banded lens is the lowest power lens. So a couple of things we can get from this. But this is what we're really interested in. Now the formula, if you call, let's do the formula up here. Distance equals, right? 1.22 times lambda over 2 NA. Now, hopefully you can see how to do this now. This number is going to be 5,000. angstroms. Can anyone calculate that for me? I'll just wait for the answer. Calculate this using these numbers. If you don't need this number, right? You don't need 4x. This is the number you need. Somebody calculate for me the distance, which is the shortest distance or the smallest distance between that this particular lens can resolve. And I'm going to wait for the answer. I expect you to do something. Get your phone out, your calculator out, and I want you to calculate the resolution of this lowest power lens. And I'm going to wait a couple seconds, a minute, maybe more than a second. I'm waiting for an answer. Very good, very good. And more than one got that. It's a third. Let's write that down. 30,500. Good job. Angstroms. Now that doesn't mean much to a lot of people, and I can understand that. So unfortunately, we're going to have to learn something else. We're going to have to be able to convert from one thing to another. You are going to have to be able to convert from one unit to another. Now, to do this, we have to know the relationship between this. And I'm going to, if I can, let's see, I don't know if I can, how neat I'm going to be, but let me give a shot over here. Let's, 1 millimeter equals 1/1000th, oh boy, this is going to be good, of a meter. Okay. 1 micrometer, and you usually rewrite it like this, equals 1/1000th of a millimeter. At least I'm going slow enough, right? It's written a little differently, weird, like an N, 1 nanometer equals 1/1000th of a micrometer, and 1 angstrom equals 1/10 of a nanometer. Well, that was hard. Yes, you should know this. So hopefully you've heard my verbally as I went along with my pen. So the next question is, a couple questions for those of you out there. How many decimal places are there between here and here? Actually, only one, because this is 1/10 of this. Good try, though. How many decimal places from here to here? That answer would be 3, because this is 1/1000th of this. And how many decimal places between here and here? Give it a shot. How many decimal places from here to here?
2.
Well, if this is 1/1000th of this, it's still going to be what? 3. Okay? When something's 1/10 of something, that's 1 decimal. If something's 100th of something, that would be 2. If something's 1/1000th, it's going to be 3. So this is what you need to know right here. Now, there are many ways to make this calculation. Many of you have already learned dimensional analysis. I'm not going to pretend to teach that here. I'm just going to give you my old-fashioned way of doing this. Gets the job done for me, but I'm not suggesting that you follow my advice. I'm suggesting to you that you need to know how to convert between these units for the test. Okay, and I'll say them again one more time. 1 millimeter equals 1/1000th of a meter. 1 micrometer equals 1/1000th of a millimeter. 1 nanometer equals 1/1000th of a micrometer. And 1 angstrom is 1/10 of a nanometer. So you can go back and write it better if you don't like the way it looks. And even if I write it without this mouse, everyone still has that problem. So I verbally did it. Okay, now I want you to convert this number to micrometers. I don't want this answer like this. I want it reduced, you might say, and I want the answer in micrometers. And there's a good reason why I want it in micrometers, because most of the things that we'll be doing through the microscope are going to be in micrometers. So can somebody convert that for me? And while you're converting, I am just going to disappear for 1 minute to turn the fan on in my office, that's all. So it means 1 minute. So I'm back here waiting for the answer. I don't see one. I want you to convert this to micrometers. I said somebody came up with 305. Well, let me ask you this question. How many decimal places are there between here and here? Someone said, oh, okay. Someone has the answer. I think they have it right. Okay. So let's look at this. My simple way. I didn't say it's you, has to be your way, just my simple way or my difficult way. I don't know. Between here and here, there's 1 plus 3, 4 decimal places. So I know that I'm going to be moving the decimal point 4. Okay? From here, I want you to convert this to micrometers. 1 plus 3 is 4. There are 4 decimal places. You can memorize it other ways. Everyone has their own way. And again, I encourage you, don't forget, tutoring is available at ACC right now online. So if you don't understand how to convert from one to the other, why don't you try to avail yourself of that? Remember, I think we talked about that the very first day. Tutoring is available. If not, look at the college webpage and find out where that is. But it's available pretty much every day, and you don't want to miss something because you were afraid to use what's available. Okay. So that's the first thing. You need to know how many decimal places. Now, there are many ways to do this, but knowing these numbers is critical. Not so much, we're not going to kill anybody by making a mistake, but the doctors, those people who have to make calculations, I know there's computer programs, but at some point, sometimes you just have to do something. And for me, when I was doing research, one of the biggest problems was I had to know which way I was diluting something, in other words. And so it was very important to understand this concept, and I had to develop my own little simple way. And so here's me. I go, okay, I know it's 4 decimal places. This diagram helps me, but also I need to know which direction am I going to move the decimal point. And again, I don't want you to use this as your methodology. I want you to go to dimensional analysis and learn this. You might call it the proper way, because I'll be honest, I don't do new math. And this is not a math course, so luckily I don't have to worry about that. So if you've learned some kind of new math, I'm kind of old-fashioned, but I get the number. And so what I say to myself is I have to always be right. So I learned a phrase. I only learned one phrase: small to large, move to the left. Am I not going from something small to something large? And the answer is yes. So I know I'm going to move the decimal point 1, 2, 3, 4 places. And so the answer will be 3 point, which some of you had, 0.5, but you said the wrong, yeah, you said it right, okay, micrometers, and I'll draw it like this. Okay? Now, some of you got other answers like 3.05 angstroms. No, because we converted it from angstroms to micrometers. And this is very important because in microscopy and in most of the images we look through the microscope, we're going to be in micrometers, okay? Now, I'm going to leave that there. We're going to move on because we don't want to, dwell on this too much. But I think, you should be able to, using whatever method you feel comfortable with, be able, if I say on a test that the image is, let's just say this was 30,500 angstroms. What is this number in micrometers? You should be able to calculate that, okay? So now look, that's only going to be 1, maybe 2 questions on a lab test. So it's not enough to get worried about. It's not enough to spend hour upon hour dealing with it. But if you want to get that perfect score on that lab test, then you want to learn how to do this. Otherwise, you're going to miss at least 1 point for sure, possibly 2. Now, let's move along with this. So at some point in the lab exercise, you'll be asked to make this conversion. Let's go back now. Let's clear this all out. This will be available because it's been being recorded. Good question. Where do we find the NA? Okay, I'm going to have to give that. You already know the NA for 10x. 4x, I apologize, right? And for the 40x, I don't know it off the top of my head, but I will figure it out. I don't want to say what I think it is. So let me look that up for you. So before we finish, in fact, no, let's not go anywhere. I will give you the information. Normally, you would look at the microscope lens to find it. And unfortunately, well, I can't magnify. This picture isn't clear enough. And so I can't do that. Maybe we'll find a picture as we go along in the rest of the lab exercise. So remind me before it's all over. I will definitely give you that number. If I can't find it, the easiest way is the internet, and just say numerical aperture for 40x objective lens. If someone wants to do that while we're doing other things, that would be great, because we could give the answer to everybody. But I don't expect you to memorize these numbers. I happen to always know the 4x, but I don't memorize them all. I can give you the one for the oil lens, but I can't give you the one for the 40x lens off the top of my head. I don't want to, again, mislead. So if someone wants to look that again up on Google while we're moving on, you would simply go numerical aperture. I would write it out. Numerical aperture for 40x objective lens. Why don't one of you do that and see what you come up with? Meanwhile, I'm going to erase this now so we can do something else. All right. Now there were some principles involved here. Maybe we can just stay with this, because this is kind of big on the screen here. We don't have to go bouncing back and forth, but I want to make it a little bit bigger. Yeah, 0.65 sounds absolutely correct. 0.65 is the numerical aperture. Thank you very much. Thank you. You see how easy it is to find information? So let's assume that this is, let's just say, it looks like the 40x lens, because it's long, and I'll just go 0.65 numerical